Hey, hello everyone. Welcome to the last lecture of this course. So in the last lecture, we started to talk about nonlinear models, and we saw that this is world as compared to the linear models. And we ended the session with a discussion of Hackett and Tobit models. So these models were used to address, for instance, selection biases when we have a subsample, yet we want to generalize our results to a larger sample. And in that case, we have to make sure that we take into a potential selection process when we evaluate our results. And well, as we've seen, like what we talked about was selection on the outcome variable. Yeah, so for instance, we had truncation or censoring on the outcome variable, and we saw that this usually introduces a bias. Now, what I want to do in the very first part is we talk a little bit about selection, but instead of talking about selection on Y, we talk about selection on the observable xi, and that sometimes under certain conditions can actually be ignored. So now let's say we have a cross section to make it the notation simple here, and we have an indicator that simply tells us whether an individual is observed in a sample or it is dropped from the sample. Now, moreover, we assume that the data follows our usual linear model, yeah, so very simple linear model. And yeah, well, of course, we know that the OLS estimator can be derived in the following way. It has exactly the form that we all know. It's just now that this S indicator is included because we have to make sure that we only look at the observations that are actually in our sample, right? So the sum goes from 1 to n, but not each of those individuals is actually observed in our sample. So now what we get is that by, as usual, replacing y according to our linear model, we get that this is equal to the true parameter that we are interested in, plus a term of which we have to make sure that this is somehow zero, yeah, or converges to zero as n goes to infinity. Now, let's also assume that if we had a random sample from the total population, everything would be fine. Namely, we assume that xi is exogenous and also that the full rank condition holds in the population. Now, if we want to identify beta from the subsample, then the first thing that we need is that the full rank condition has to hold in the subsample. Yeah? So when we only look at the observations where the indicator is 1. Well, that's pretty clear because as n goes to infinity, this object here converges to this, right? And yeah, so if this, of course, does not have full rank, this thing does not exist, and therefore the OLS estimator does not exist. Now, for instance, when could that be violated? Well, let's say that we have, of course, in our population, there's males and females. However, in our subsample, there may only be females. And yet we forget about that and we include a gender dummy in order to test for differences between males and females. Now, of course, since the sample is only females, that gender dummy will introduce perfect collinearity, and therefore this inverse matrix here will not exist. Okay. Next, for consistency, we also need that, well, this thing here goes to 0. So we need that the expectation of this is 0. And well, a pretty famous assumption that ensures that is this missing completely at random assumption, where we assume that this indicator S is completely independent of X and epsilon. Yeah? So that's completely missing at random. When we have independence between S and the two other variables, then of course, like the expectation that we see here factorizes, and we know that X is orthogonal to epsilon in the population. So this thing here will be 0, and therefore this condition here will be satisfied. Now, missing completely at random, this may be relatively strong. However, we can make this slightly weaker by assuming that we have this exogeneity, not only conditional on the X, but also on this indicator S. And this is known as exogenous sampling. And well, this assumption can hold, for instance, if like the X is exogenous in the population, as we have assumed, and the SI is a deterministic function of the X. And in that case, this condition here would be satisfied. Okay. Now, another thing that is important is that when we take our subsample, then we don't want to introduce correlation between the observed X and the unobserved epsilon. Yeah, so for instance, let's assume that we have a wage regression. So we want to see the effect of education on wage. And of course, in epsilon, we have hidden variables such as motivation. And now let's assume for the moment that in the population, education and motivation are actually uncorrelated, in which case, given a random sample, this regression here would yield consistent results. So because like education is uncorrelated with the error term. Now, let's, however, look at a subsample from the population where we only consider people that are currently working. And now this result is actually taken from the Wooldridge book. So he explains that if you look at the average motivation of workers with low level of education, then the average motivation is likely to be higher in your subsample than in the full population. And the intuition here is that if you have a low level of education and you're kind of only averagely motivated or even less than that, then you are less likely to end up in our sample because simply you are less likely to actually have a job. Thus, if you follow that logic, in our selected subsample, there is a correlation between education and motivation. Remember, this is hidden in the error term, which does not exist in the population. So if we had a random sample from the population, everything fine, OLS works. However, in our selected subsample, education is correlated with the model error, and therefore this condition here holds. Yeah, so like yeah, basically OLS will be inconsistent because in our subsample we have endogeneity. Now, another example that I took from this paper here is about Hollywood stars. So let's suppose, for instance, in the population, in the general population, there is no correlation between beauty and talent. Let's say acting talent. So in the population, there is no correlation whatsoever, which sounds rather plausible. And both talent and beauty cause Hollywood success. So if you're very beautiful, you make it in Hollywood. And also if you're very talented, you also make it there. And of course, if you're both, however, your chances are bad if you have neither of those. Now, let's say we want to assess again the effect of talent on wage. Okay, now, of course, we don't control for beauty, so beauty goes into the model error. However, like if we have a random sample from the full population, there's no problem, right? Because we know that talent and beauty are uncorrelated in the population. Now, like in comparison to that, let's say that we have a sample of Hollywood actors. Now, again, in the population, beauty and talent are uncorrelated. However, if we look at this subsample, talent and beauty are actually related. They are correlated because we know any person that doesn't have talent and is in our sample must be beautiful. So therefore, kind of knowing one thing gives you information about the other. And thus, in our selected subsample of successful Hollywood actors, there is a correlation between talent and beauty that does not exist in the full population. And thus, in our selected subsample, OLS will yield biased results. Okay, so this was a little bit on selection. And now we want to continue with a type of nonlinear data, nonlinear model, when we model count data. So count data, as the name suggests, is simply non-negative integers, 1, 2, 3, 4, and so forth. Yeah, right? I mean, that the name is pretty obvious. And I think like the first example is probably one of the most popular applications when you look at patents granted per year. You can, of course, model other things like doctor visits or cigarettes smoked. Importantly, there is normally not really a natural upper bound. So in principle, you can have 10 million patents per year in principle. Of course, the chance of that is very low. And the outcome is 0 for some members of the population. And we will see later that the zeros, they can actually cause a problem in applications, but we will come to that. Okay, so now let's assume that y is a count variable, so 1, 2, 3, 4, and so on. And we have also a vector of explanatory variables as usual. And we want to model the conditional expectation of y given x, as we always do. Now, what you could, of course, try is that you fit a linear model, right? This thing we always see when we look at linear models. So let's try to fit a linear model. However, the downside of linear models is that it can produce negative predictions. So that your count variable happens to be negative. And that, of course, doesn't really make sense knowing the nature of y. So that's the downside of the linear model. Now, when you look at practical applications, people say, okay, well, I mean, I modeled this non-negativity of the count data, so I still want to use some sort of a linear model because I know how to use it. However, I want to take into account that the data on the left-hand side is always positive. Now, what they do is, well, they first try to fit the log. We model a linear function for the logarithm of y instead of y itself. And then sometimes people run into the problem that y is equal to 0 for at least some individuals in our sample. And we know that the logarithm of 0 is not defined. It's like going to minus infinity, right? So in order to circumvent this problem, what people do is that they simply add 1 to each of the yi's. So kind of like, of course, intuitively, this seems to make sense, right? I mean, you simply add the same amount to each of the response data variables. So what can go wrong? Well, a couple of things can go wrong, of course. First of all, it is not the same kind of modeling the log than modeling y itself. So because the log is nonlinear, we cannot simply take out the log out of the expectation and it stays the same. So there's no equality here. And normally we're interested in this. And when we model the log of y, what we do here, it is not simply the same as the log of our thing of interest. So we want to have this because then we can transform back to obtain this. But we cannot obtain the right-hand side from the left-hand side. Moreover, when you do this log on the left-hand side, then we know that normally we would interpret the betas with this percentage change interpretation, right? However, this percentage change interpretation actually does not really work so well because like this percentage change interpretation only works for small changes in X. And here we have jumps. So that is not really appropriate. And finally, when you do the log plus 1, you can actually find spurious results. So you find a result that is not actually there. So this is, of course, a pretty subtle point. So let's go through an example where we want to show that a certain treatment has actually a differential effect on two groups, and the difference is considered in relative terms, right? So for instance, if the treatment doubles each group's patterns, that is actually the, yeah, exactly. Yeah, so we go through this example, then there is no difference in the relative effect between the two groups. Okay, let's go through the example. Let's say the first group has a patent average of 1 and the second group has an average of 10. And now we assume that the treatment doubles the number of patents in both groups so that there is no difference in the relative impact on both groups. So we actually do not have a result. There is no differential effect on the two groups of the treatment. Now, if you do the plus 1, then the group 1 goes from 2 to 3, whereas group 2 goes from 10 to 21. And we see that here this increases by 50%, this increases by almost 100%, and thus you see that indeed the treatment seems to have a different effect on the two groups. Yeah, so by doing this log+1 transformation, we actually created a result that was not there initially. Okay, now these were the downsides of the log transformation and on, well, what some people use in practice. However, most people nowadays say that the best approach is probably to simply model this thing, yeah, the conditional expectation of y given x directly, while taking into account that yit is a count variable. Well, now, what is the most famous distribution for count data? Well, it's the Poisson distribution. So therefore, the most popular choice is probably the Poisson model, where we assume that y given x is Poisson distributed with some mean that depends on x. Yeah, and then like, okay, here, this is pretty much simply the PDF of the Poisson distribution. It's given like that. And we see that it depends on the mean here and here. And the mean is modeled as a function of x that is always positive. Yeah? So the most popular choice is this exponential specification. Yeah? Of course, because, well, if y is a count variable and it's Poisson distributed, we know that all of the y's are positive. Therefore, we have to ensure that also the mean is positive. And we do this by this exponential function here. Okay, now the next thing is simply a little bit of notation, right? So if we are in a panel and we pool everything together, we assume independence across I, we assume independence across T, then, well, the joint likelihood is simply the product of the individual likelihoods in each little t. So very simple here. Now we take logs, and this is what we get. So this part here actually does not depend on beta, so we can ignore it. It doesn't play any role in the maximization. So thus, the likelihood, the log likelihood is typically written like this. So we simply ignore parts that don't play a role for maximization. Okay, now we look at the first order condition, so that's simply taking the derivative. So we take the derivative with respect to beta, then we have this thing here stays, and here we have the x coming in front, because we're taking the derivative of the exponential. We take the x common, and this is what we get. Now, we also want to know whether the likelihood is actually concave. The only thing that we need to do is take the second derivative. Now, if we do this, we see this part here again does not depend on beta, so we only have to care about this part multiplied by xit. And what we get is, well, this is always positive. This is also kind of like positive definite if this thing has full rank. So the minus here in front makes everything negative, which implies that the Poisson likelihood is actually nicely concave, and thus the MLE is the unique maximizer of the likelihood. Okay, now what do we do with the results of this Poisson model? Well, normally we are interested in the marginal effects. Yeah? So the coefficients don't give us necessarily a direct interpretation, so we look at the marginal effects. Now, if we take the derivative with respect to the cave component of x, that's pretty simple here. Yeah? So we take a derivative of the exponential. This particular component comes to the front. So this should actually be the beta k. Okay, so what happens is that the marginal effects, that does not only depend on the parameter, but also on the level of the axis. Yeah? So we had this before. In nonlinear models, the marginal effects, they actually depend on the level of the x variables, and therefore they are not constant. Yeah? This is the big difference to linear models. Normally, we would then take the average over our sample to calculate, for instance, average partial effects or average marginal effects. However, here we can actually see that in the Poisson, we have an easier interpretation. Yeah, so when you look at this, we take the derivative of this and we divide it again by this part here. Yeah, so we take the derivative here and divide it by this. Then, of course, we can write this as the derivative of the log. Yeah. So again, this is a typo. This should be the beta k. So if you consider this derivative with the beta k here, and you divide it by this, of course, what you end up with is the beta k. And the beta k itself is the derivative with respect to x of the log of the conditional mean. And therefore, again, 100 times beta k can be interpreted as the semi-elasticity. Yeah, so the beta k actually does have a percentage change interpretation as we had in linear models when we take the log on the left-hand side. Yeah, so this is very nice. The Poisson is, in terms of interpretation, pretty similar to linear models. Now, there's more things that are very similar between the Poisson model and linear models. Namely, if we look at the residuals, yeah, so yit minus its conditional mean, that is simply this thing here, then our first order condition here, so this is kind of the residual. The first order condition implies that the residuals are orthogonal to the axis in the sample. And this is something that we have seen in linear models. So this reminds us of linear models. And this leads us to another similarity between the linear model and the Poisson model. In the linear model, we only need to correctly specify the conditional mean for consistency, right? The same is true for the Poisson model. So if we are confident in our specification of the conditional mean of y, then we know that the Poisson maximum likelihood will be consistent. And this is actually something that is quite different from other nonlinear models. Yeah? So for instance, if you look at Logit and Probit, in Logit and Probit, you have to be confident that the full distribution that you specify on the model error is correct. Yeah, so if, for instance, only the conditional mean is correctly specified, but like the variance is not correctly specified, in Logit Probit, you will get inconsistency, whereas in Poisson, you get consistent estimates. And so this is like a nice robustness property. And because of that, we only need to correctly specify the conditional mean. What people do many times is that you estimate the coefficients with Poisson maximum likelihood. Yeah, those are consistent as long as the conditional mean is correctly specified. Nevertheless, you don't really trust in your standard errors derived from maximum likelihood, because you say, well, you know, the conditional mean is correctly specified, but I'm not sure if the distribution is really fully Poisson. Maybe only the mean is like a Poisson, but not the variance and not the higher moments. So what you could do is that the coefficients estimated with Poisson are consistent, and then you do robust sandwich estimation for the standard errors. And this is, again, really as if it was a linear model. So what do people do? Well, first of all, what happens under correct specification of the likelihood? Well, what we've learned when we discussed asymptotic normality is that, well, the estimator, the MLE, centered by the true value, scaled by square root nt, converges to a normal distribution with mean 0 and the inverse Fisher information as the asymptotic variance. Now, if the likelihood is, for instance, not completely correctly specified, meaning that only the mean is correctly specified, but not any higher moments. Yeah, so that is kind of this case here. In that case, we know that the information equality would not hold. Yeah, so for the information equality, we need that the likelihood is correctly specified. In that case, if you go back to our asymptotic normality proof, the asymptotic variance of the misspecified MLE actually has this sandwich form. Yeah, so F is still the Fisher information, and here we have the Hessian, kind of like the negative expected Hessian. Okay, so what would you do? Sorry, yeah, well, I should explain this here. What you would do is that you estimate the coefficients with Poisson, but the standard errors you estimate with a robust sandwich estimator. So you estimate the Hessian. This can easily be done. Well, so take the second derivative of the likelihood. Then you estimate the Fisher information, the square of the score, yeah, this thing here. And then you do this sandwich estimation. And this will then be consistent for the standard errors, even under misspecification. Yeah, so this is a very nice robustness property of the Poisson model. However, the Poisson also has downsides, which make it like not really applicable in certain models. So for instance, the Poisson distribution, like the density, implies that the mean is mu and the variance is also mu. Yeah, so the mean is exactly the same as the variance. Normally, if you look, for instance, at Wikipedia, the mean is lambda and the variance is also lambda. This is something known as equidispersion. And when can it be problematic? Well, whenever you have like an application where there are excess zeros. And this is very classic when you analyze the number of patents, because most firms, or like a large chunk of firms, actually has 0 patents in a year. Many firms do not patent in a year, and some firms patent a lot. So you have excess zeros and you have over dispersion. Yeah? Okay, let's talk a little bit more about the case of excess zeros. So let's, for instance, assume that x is a Poisson variable and y behaves like a Poisson variable whenever y is positive. Yeah, so for anything larger than 0, y behaves as if it was a Poisson variable. Yet, if we have excess zeros, that means like the probability of observing zeros for the variable y is larger than the probability for the Poisson variable x, then this immediately implies that the variance of y is larger than its expectation, and therefore the Poisson model is of course not appropriate because, well, the Poisson immediately implies that both are equal. So what are the alternatives? Well, a very popular alternative is this negative binomial model, which is used both in the presence of excess zeros, but actually mostly when overdispersion is present. So like, well, the variance is larger than the mean. For the excess zeros, we will look at the zero inflated Poisson in a second. Now, in the negative binomial model, what you assume is that, well, y still follows a Poisson model, yeah, so it's still count data, you take that into account. However, your lambda, meaning like what you specify normally as the mean, is multiplied with the CI. And CI itself is a random variable. Yeah, so M is like our model for the mean, the conditional mean. For instance, like our usual, what do we have here? Exponential, yeah. And CI is a random variable that follows a gamma distribution. It can then be shown, so we don't go through here the whole calculations. You can actually check this out in Cameron and Trivedi, so they do a very nice exposition of these models. It can be shown that our yi then doesn't have a Poisson distribution, but it has p. And well, what does the negative binomial normally measure? Well, it represents the number of failures which occur in a sequence of Bernoulli trials with success probability p before the target number of success r is reached. Okay, well, I was just reading the sentence. Now, let's do an example. let's say we define that rolling a 6 is a failure and everything else is a success. Yeah, so then negative binomial 3, 1 over 6. Um, okay, sorry, this should actually be 5 over 6 because it's the success probability. Sorry, I have to fix that. Yeah, so we are kind of rolling a dice until the third 6 appears. Yeah? And the negative binomial would give us the distribution of the number of rolls that we will likely have, right? So give us a probability, for instance, for 10 dice rolls or 12 or 200. Now, the advantage of the negative binomial over the Poisson is precisely here. Yeah, so this is the expression for the mean of a negative binomial model. And this does not coincide with the variance of a negative binomial model. So therefore, unlike in the Poisson case, we can allow for differences between the mean and the variance. And therefore, we can allow for over-dispersion in the data. Finally, particularly when we have excess zeros, so when the data behaves pretty much like a Poisson model for everything that is above 0, but we have far too many zeros in order to fit a Poisson model, we can fit a zero-inflated Poisson. And the same idea is applied with many other models as well. Yeah? So here we only do a very rough sketch. So the idea is that we have one distribution that generates the zeros. And then for anything that is non-zero, the process follows again a Poisson distribution. And this is precisely what is written here. Yeah, so we have a particular distribution for the case that y is 0. And for anything else, yeah, for the remaining part, we simply use the Poisson distribution for y as we had before. And well, as in the Poisson model, we specify lambda, which is the mean, like this, in order to ensure that the mean is always positive. Okay, so this was a little bit about more selection and count data models. So we did very little about count data. So that's a whole universe of models out there. So we only did like a very rough sketch. And in the next part of the lecture, we want to talk about how to include unobserved individual heterogeneity into our nonlinear panel models. Okay, see you there.